Hello everyone, welcome to our web TV studio. I'm Thomas Porches, I'm an application engineer at Teledyne E2V. I'm responsible for the digital product line, that means processors, memories, and processing modules. So I hope you can hear me well, that the audio is fine. We've got a chat way of discussing together. So when you put things, message in chat, I get them on this iPad. So tell me and just say hi if you hear me correctly. And in the meantime, I'll continue. I'll present you the way this session is going to go. So this should have been a physical session at Electronica. But due to the situation, this was cancelled and transformed into a virtual event. So the objective is to show you in practice the demonstration that we've put together for this event. The focus in this session will be on power optimized parts from Teledyne E2V that helps our customer reducing power consumption or ease thermal management. So we will proceed first with a 5 minutes video, pre-recorded video of the demonstration. So you'll see the demonstration and the results. And after those 5 minutes, we will get back to the live, and you'll have the opportunity to ask any question on the chat, and I'll attempt to answer the questions later on. Any questions, technical or non-technical questions that you would have. So we'll now launch the video, and I'll talk to you in 5 minutes. Thank you. Welcome everyone. Today, I'd like to exhibit a demonstration that we have put together to show you in practice how you can save power and simplify thermal management in high-reliability processing systems, so that you can see with your own eyes the possibilities that we offer at Teledyne E2V. At Teledyne E2V, we receive frequent customer requests to deliver power-optimized processors. Sometimes the need is to reduce power consumption because of power supply sizing or because of limited power available. In drones application, for instance. Sometimes the requirement is of compactness because it's not possible to cool properly the components within the given volume constraints. A few months ago, we published a white paper that explains in detail how we managed to reduce by 46% the power consumption compared to the datasheet power consumption on a specific customer application. Today, I'd like to show you in practice the benefits that it brings. Before going in the details of our demonstration, I would like to give you some details on how to analyze processor power consumption. Processor power consumption is typically split between what we call static power consumption and dynamic power consumption. So on this graph, dynamic is the yellow one and static is the blue one. What you have to know about static power consumption is that it more or less corresponds to the leakage current that is flowing through the device as soon as you apply power supplies on it, even if in reset state and even if there's no clock applied. Static power consumption evolves non-linearly versus temperature. And what's interesting about static power consumption is that it's not repeatable across parts. That means it's possible to select parts that have lower power consumption. Dynamic power consumption, on the other hand, is more or less independent from junction temperature, but it is dependent on CPU load, platform and CPU frequency, and the types of peripherals that you are using. That means that dynamic power consumption is dependent on your application. Now, let's go in the details of our demonstration. We have two single-board computers that have been designed by our partner Syntex. On each single-board computer, we've got a T1042 processor that is a quad-core PowerPC architecture that can run up to 1.5 GHz. The left processor is a standard processor that is running an application that loads the CPU at 100%. The right processor is a Teledyne E2V power optimized processor that runs an application that loads the CPU at 50% load. We've got an infrared camera from our colleagues at Teledyne DALSA that is looking at both processors simultaneously, and the camera picture is displayed on this screen. So we've got still on the left the standard processor, and on the right the Teledyne E2V power optimized processor. So now looking at the details of the results. So if we look at the left processor, we've got a temperature, the heatsink temperature is around 71 degrees, and the right processor is around 59 degrees, so around 12 degrees of difference. As you've probably realized, the junction temperature is actually higher, and this is what we see on the terminals. We see that the processors are between 90 and 100 degrees of junction temperature. So there is still a very big difference in terms of junction temperature between both processors. Looking at the junction temperature and the board power consumption, so board power consumption, we've got 10 watts on the left board, and we've got around 9 watts on the right board. And if we look in the details of the processor power consumption, which is of interest here, we see that the difference between the two processors is between 1.5 to 2 watts, which is quite a very big difference. So, to conclude today, what we have shown is how it's possible to reduce power consumption in your high reliability processing system thanks to our products. What we have shown is when keeping the same heatsink, it's possible to reduce power consumption. But it's important to note that it's also possible to reverse the approach and to keep the power consumption fixed and to reduce the heatsink size. If you want to get in more technical details on how power optimized processor products can help you, don't hesitate to have a look at our white paper and to get in touch with us. Welcome back. So my colleague Thomas joined me for the question and answer session. So again, you have the opportunity to send us questions over the chat, and we'll do our best to answer. Perhaps
there's often a question I have on or that our customers are having about how we do differentiate compared to NXP. What is the value we add? So we are working on safety critical processors. We are working on high reliability processors. But could you explain how we differentiate compared to NXP?
Sure. Yeah, indeed, it's a good point, because people don't always know exactly, they don't always understand exactly what we are doing at Teledyne E2V and how we compete or how we compare with NXP. I can share a few slides that we've shared back in April from our press conference to show you what's differentiating us from NXP. And what's important first to know before I go to the slides is that NXP is providing parts for mostly consumer applications, while at Teledyne E2V, what we do is we focus on high reliability application. That means aerospace, defense, space applications, and railway. And all those applications, they require very specific needs for the parts. So to answer those needs, that's where we locate our offer, if I can say, and that's where we differentiate from NXP. So mainly, our differentiators are based on environmental constraints that the customer have in those applications, in those specific applications. So I'll just jump to the end of this presentation. Yeah. here we have, so I would say we have 4 main topics or items on which we differentiate from NXP. And the first one is the capability to bring those components to extended temperature ranges. So typically, the temperature range that the parts from NXP would operate at would be between 0 to 105, or sometimes some of the parts from -40 to 105 degrees. And we extend this temperature range, and we are able to deliver functionally equivalent parts from NXP, but that work up to -55 to 125 degrees, and that's really important for our customers. Obviously, this is not an easy thing to do, and we have first to qualify the part and verify that it can actually withstand this harsh environment. And once this is done, we can then provide parts and deliver parts to our customers. The second important thing is leaded, what we call leaded option, so it's deballing and reballing of BGA packages. Now it's only possible to procure at NXP ROHS parts, so that means lead-free parts. And for some of our customers, it's still very important, especially in space or in defense, to deliver parts with leaded versions. So we are able, again, to do this deballing and reballing, and most importantly, we are able to qualify this process, because this process can be harmful to the processor, because it makes some stress on the component, and we are able to actually do this process and qualify this process to demonstrate that the part is working as well and is as reliable afterwards than it was before. And then we are able to deliver those parts, leaded parts, to our customer. The third thing is custom solutions, and that's the focus of today's discussion, specifically on power screening, but we can do other things. And the final point is the point for which we've been known, let's say historically, the extended lifetime support, because our customers, well, aerospace and defense and space markets, they usually want to be able to provide their products for extended lifetime. That means like 15 to 20 years most of the time. And to do that, they have to be able to procure the part for this extended lifetime. And that's also a service that we offer. We have the capabilities to store the parts safely in a controlled environment so that they don't deteriorate over time, and so on. So now that I've introduced a little bit more about what we do at Teledyne E2V. So we've got testing capabilities, and we've got also what we call a factory. And at this factory, we have assembly lines, semiconductor assembly lines. So we are capable of taking wafers, and from wafers to dice the die, and to build completely parts from silicon. Thomas, do we have any question on the chat?
We don't have any question, but I'm interested if you could explain what I think at the end of the demonstration, so you speak first about power consumption, and I think at the end of the demonstration, you were mentioning something like we could do the opposite of the reverse. It's like we could reduce the heatsink size.
Okay.
I'd like to understand a bit more about that, because that's something we do not mention too much during the demonstration.
Okay, so I think to answer your question and to illustrate that to our auditors, I'd like to show a few slides on how to reduce heatsink size, so that I can illustrate with figures how this can be done. So indeed, at the end of the video, I was mentioning that what we've shown is we keep the heatsink the same, and we focus on power reduction in this demonstration. However, some of the customers don't bother about the actual power consumption, but they bother more about the heatsink requirements, because sometimes it just doesn't fit in their volume constraints. And in that case, it's also possible to use the power optimized parts that we are able to deliver to reduce the heatsink size while keeping the power consumption constant. And to do that, well, if we get back to the typical example, the typical power consumption evolution versus junction temperature, we remember that it's nonlinear versus this junction temperature. Well, when we look at the power optimized part, we see that at very low temperature, it's almost the same because it's very close to zero. And the higher we go in junction temperature, the larger the gap grows. And that's very interesting, because that means that if you select a power consumption set point, for instance, 8 watts, well, you see that the standard processor in blue cannot operate above 107 degrees C without exceeding this power consumption limit, while the other processor, the power optimized one, can work something like 10 degrees junction temperature more before exceeding this power consumption limit. So that means that if we do simple math on calculating the thermal resistance of the heatsinks, well, taking a ambient temperature of 70 degrees and this limit of 8 watts, well, that leads us to a maximum thermal resistance for the heatsink of 4.6 degree per watt for the standard processor, and for the power optimized processor, that leaves more room to have a smaller and lighter heatsink, because you can have a heatsink that requires a maximum of 6 degree per watt. So that means that the heatsink design is simplified by something like 30%. So general idea is that, well, by reducing the thermal resistance of the heatsink, thermal designers, they understand that you can gain in terms of size and weight of your cooling system.
Thank you. I have a question from Mike Lansinger. What part is Teledyne offering power screening on?
It's an excellent question, actually. I would say any parts and none. Actually, it's not something that we offer off the shelf. So if you look at our datasheet, you're not going to find any part that is stamped as low power or power optimized. The way we work with our customers is that we always have to go through an analysis with them, a discussion with them. So technically, it's feasible to apply the same technique on any of the processors of our portfolio. But if you want to know more, you have to discuss with us, because it's not something that is easy for which it's easy to assess feasibility, and we prefer to go through a discussion with the customer. Perhaps to illustrate that, we're going to show a few slides on what is the process to actually deliver power optimized part to customers, so that you see which steps we go through and which discussions we have with the customers to be able ultimately to deliver those power optimized parts. And you will see that, well, the process is not very complicated, but it can take a bit of time to understand if it's feasible. So the first step will be obviously in the initial contact to have a first discussion with the customer to assess if it seems viable. We have to understand if the customer wants to focus on power reduction or on heatsink reduction. We have to understand how low he wants to go. If a customer wants to reduce by 10 the power consumption of a processor, obviously it's not something we are going to be able to support, because that's not physically realistic. Once we've assessed with the customer that it's worth continuing the discussion because we can really say something wise on this, well, we'll guide the customer to do some dynamic power consumption measurement. And why this step is very important? Because this step helps us to understand how much power the customer application is requiring on the processor. And that will help us further to then evaluate the maximum static power consumption, because what we do at Teledyne E2V is select parts that have a limit on the maximum static power consumption. So to get this maximum static power consumption threshold, well, it's simple math because the customer knows how much power budget he can allocate to the whole processor. Since we've made measurements together, we know how much dynamic power consumption the application require. So we subtract total power minus dynamic power consumption, and we get the maximum limit for the static power consumption. And based on this, we do some analysis internally on our data, based on our database and based on our experience with those components to see if it's feasible to go as low as the application require or not. And if it's a go and we realize that we can actually commit to deliver those parts, well, what we're going to do is we're going to do some sampling and select some parts that we have in stock and that are close to this maximum static power consumption limit. And we're going to deliver those parts to the customer to do again some measurements. So this time, the customer will assemble our parts on their boards. They will operate the boards at maximum operating temperature with their application. The objective in there is really to check that the solution is viable and that they don't exceed in practice the total power consumption budget that they allocated initially. And if that's successful, well, we can start actually to select parts, but in mass production, and to deliver them to our customers.
Would you be able to put a timeline on this complete process?
So I would say it's very dangerous to talk about timeline in this process because most of the time it depends on where we are when we start, where the customer is, sorry, when we start the discussion. So sometimes the customer comes at a late design phase and he wants that little extra margin to be safe in its application. So in that case, well, the customer already has some boards that have been designed, so he's able to do some measurements very quickly. He's able to do again some measurements quite quickly, so it can be only a few months when the design is already finished. But sometimes the customer already know at the early phase of its project that thermal management or power management is going to be an issue, and he contacts us at the beginning. And in that case, well, obviously, this is going to go through the development phase of the customer's project, which can be in the application that we target up to a few years, actually. So it's really dependent on the customer. But what we have to say is that we can provide quick support. We can talk with customers over conference to evaluate their needs. Then we are able to select and ship parts quite quickly whenever it's standard parts and not two particular parts. Otherwise, we have to buy parts from NXP, which takes a bit longer. So it's really customer dependent, the lead time of applying such process.
So is there any advice you would like to give to customers working with our processors?
Well, I would say the first advice that we would give is indeed get to know us, get to know which margin we can provide you in your design, and that will help you through the design phase. Maybe at the beginning you won't think you require our services, and maybe at the end you'll need that little extra margin that we can offer. And for you, it's like a secure safety belt, I would say, because if you arrive at the end of your project and you realize you need 10, 15, 20, or 30% less power consumption, this is something we can help you with. And I think it's worth noticing that at the beginning of your project.
Do you have examples of projects in your market that you've been helping so far?
Yeah, well, I would say the the most evident success story, we cannot share the customer name, but it's a big avionic customer in Europe. And for that customer, and this is what we relate what we demonstrate in the white paper, we worked on the T1042 processor. So that one is a best seller in the avionics market, I would say. And for this customer, we managed to reduce by 46% the power consumption compared to the values that are announced in the datasheet. So that's a huge drop of the power consumption. So we've helped them with that, and we are about to start mass production with them. So it's really a success story. And we have a few other examples on the. Mike was asking before which part can we do that on. Well, we can do any parts, but we've had requests already on the T2180, which is also a famous guy for avionics and defense. And we also got lately, some requests on the T4240 parts because that one is a very big guy and consumes quite a lot of power. And people are interested, obviously, to gain some watts in this power consumption.
So what I understand is that you're getting questions on a lot of processors that are in production since some time already, yes, and on which customers have been doing some designs and maybe potentially are arriving to a stage where they face problems.
Yeah. Well, usually what should be pointed out is that our role is not to tell customers that you should use that part and you should not use that part. Well, it's the customer's choice to use any part they want. And our services is to try to follow them and to help them, support them in using this part in their environment. And if that means reducing power consumption, this is something we can offer.
Okay, but you mentioned the 46% reduction, and why it was not shown as 46% reduction in the demonstration you had? It was a bit less, if I'm correct.
Yeah, actually, I have prepared some slides because I was expecting that question, why the demo doesn't show 46% of power reduction. And in fact, well, there are two main reasons. So on the demonstration that we've shown in the video, we get between 1.5 to 2 watt reduction. So that corresponds to 25% reduction. So indeed, if you do the math, you see that 21% are missing. So where are those 21%? And well, the first reason is, as I've mentioned earlier, the gap between the standard part and the power optimized part is growing as the junction temperature is growing. So that means that in the application, in the demonstration that we've shown today, we are working not above 105 degrees. So if we would go up to 125 degrees C, the gain, thanks to the power optimization, would be even larger. And the second reason is that in what we've demonstrated and what is explained in the white paper, the customer application is quite different. In what we have shown today, we've shown a combination of dynamic power consumption reduction because the application is only requesting 50% CPU load versus the datasheet power, so that means 100% CPU load. But in the white paper, the customer, this big avionic customer, was only requiring to use a single core out of the 4 cores available. So an equivalent 25% CPU load. And that means that compared to the datasheet power, this also helped to gain some percent of power reduction.
Why is the specification, in the case you mentioned about the 46%, why is the original datasheet not mentioning a better value compared to that? Do you know a bit about that? Why
the
it's
reason
not giving
is
a best case, I would say?
Yeah. Well, in NXP datasheets, you get key figures of the power consumption depending on the junction temperature, and there is usually two let's say set points, working set points. There's the what they call maximum, and maximum is really 100% of the cores are used, and there's what they call thermal, and it's only 70% of the core used. But generally, what we've realized when discussing with customers is that on multi-core processors, it's quite difficult to actually use at a high CPU load all cores of the SoC, of the system on chip, because it's difficult to get parallel actions of all process. So that means that in practice, it's very rare to have applications that can request even 70% of the whole CPU load. And that's where we have to help the customer and to guide them to assess this dynamic power consumption, because it is indeed not something that you can get in the datasheet. You have to do measurements, actual measurements, to get close to that. And actually, for those measurements, I didn't say before, but in the case where customers don't yet have some boards, there is always the possibility to make measurements on development kits or on development platforms, to do some measurements with a representative application to get a feeling on how much the dynamic consumption will be.
Is this something you can do also on your space processors?
So theoretically, it's definitely something we could apply to space processors. We've been having that question regularly, but with no, let's say, serious follow-up up to now. But I think this will become more and more frequent questions, because indeed the space application not only require radiation tolerance, specific manufacturing flow, but they also require lower power consumption, especially when we are talking about CubeSat application, where the power is really limited, and in those cases, the processor power can be one of the major contributor in the whole power budget of the satellite.
Okay, so I know we had that question about what processors can Teledyne offer, but I don't think we spoke about ARM-based processor, which is somehow a new trend also from NXP. Can you do also the same?
Yeah, we could apply the same. Indeed, in our portfolio, there is also the Layerscape family. And in this Layerscape family, for instance, we have the LS1046, which is a quad-core ARM-based Cortex A72. This one is quite a powerful component, can achieve up to 30,000 DMIPS. So that's quite a big computing capability. And what we've shown for power architecture is also something we could apply for ARM architecture. The concept of what we are proposing to do is based on realizing that static power consumption on the processors is something that is not really repeatable across parts. So that means that if I buy, let's say, 100 parts, well, I can pick some of the parts to have lower power consumption than the others, and that might help some of our customers in those harsh environments.
Thank you. We are not too far from the end of that session. I'd like maybe to finish by any advice you would like to give to project management people, designers working on safety critical application, high reliability application. Any advice you would like to share with them on the way they can contact you in case of help needed?
Well, obviously, I would just firstly point you out to our white paper to dig into the details of what we are doing, because this is not magic, this is physics, and everything that we do is not something out of the blue, and you will see how it works in practice. And then you can have a direct contact with me or with Thomas. We'll share, before leaving the live session, we'll share our contact details on the screen. But before we close the session, if we don't have any other question, there is one thing I'd like to show you, because today we still have this demonstration that is running behind us. And on this demonstration that is running, we've got the comparison of the processors in the same conditions. And that's something I wanted to close the session on, because this is something we can be challenged on. People may say, okay, you show two processors, one is from Teledyne E2V, the other one is a standard one, but you're not running the same application on both processors, so it's obvious that the processor that you run only at 50% CPU load is going to be colder and consume less. So what I wanted to show you is that that's correct. The combination that we've shown in the demonstration and in the white paper is both the gain from the dynamic power consumption reduction and the static power consumption reduction. But here in the demonstration, what we show is we are running the same application on both processors. And both processors here are running at 100% CPU load. So here we are comparing really apple to apple. And in that case, well, you can still see that there is something like 9 degrees or 10 degrees in the heatsink temperature of both processors. So our processor, our Teledyne E2V processor, is much colder than the other one. And if we look at the estimated power consumption for the processors, well, we see that the left processor, so the standard one, is around 6.8 watts, while the other one is around 6 watts. So we are gaining something like 0.7, 0.8 watts, and it's only at 104 degrees. So that means if you would use those processors at 125 degrees, you would gain even more, a bit more than 1 watt actually in terms of static power consumption. And that means like it's more than 10% of power reduction only by looking and selecting parts with a lower static power consumption. And this is not application dependent. It's really for the same application. So that's what I wanted to conclude on. And except if we have any other question, then indeed we will share with you the slides that show our contact detail. And if you're interested in what we do in those power optimized parts, well, you should definitely get in touch with us. So thank you for attending this live session. I hope you enjoyed and we showed you interesting things. And I wish you a nice evening or a good day, depending on where you are. Thank you and bye-bye.
Thank you.